Good morning, students. 51 are present. Good morning, good morning. That's okay. I have an extension file where I'll get the attendance who are all present. Thank you. So you need not just type good morning, thank you, because we'll have the status there. Anyways, I'll be calling in between just to check whether you're there or not. Shall we start? Should we wait or we'll start? Let me know. Should I start the class? Because I don't understand. You are at home. Why is that you have difficulty to join the meeting at 9? Not the ones, those who are there. I'm talking about those who are not there. Okay, we'll start our class instead of wasting time and waiting for those who are not punctual. Okay. All right. So just for your information, let your friends know that I have posted a link of live stream in WhatsApp. So as you know, as you might be aware that Google allows only 100 in the Google meeting. So the latecomers, after 100, those who are not able to join the meeting, they can use the live stream link that has been posted in WhatsApp. So if your friends ask you, please tell them to log in through that link that is provided. 100 till 100, it is allowed. Okay. So now we are 78 present here. Another 30, 28 will be allowed to join. So after that, if any of your friends contact you, just give them suggestion. All right, we'll start our class. So welcome to this lecture 17. Assuming that you have gone through all the recorded sessions that has been posted, but I'm yet aware that most of you have not watched. It shows that I have only views. Let me check the views. 53 views. All right. So please, I request you to go through the videos. And just for your information, I will be disabling all the YouTubes or the lectures that are posted 1 week before your internals. Okay. So I'm aware that internal dates are not yet announced, but once it is announced, before 1 week, I will disable all the lectures. Okay. So it will be your responsibility to go through the textbook and understand the topic and learn by yourself. I'm sure you are efficient enough to learn by yourself. That's the reason you're not watching the lectures, right? Okay, so let's move on. So in this session, we will be describing gate trigger circuit of an SCR. You'll be able to list them, the different gate trigger circuits. And in detail, we'll be explaining what is resistor firing circuit, or also called resistor trigger circuit. Okay. So at this juncture, you should be aware that we are talking about power electronics and power electronics application circuits, where we are talking about high power, where all applications will be of high voltage, high current that will be handled. All right. So in that applications, we are talking about this SCR, which is our power semiconductor device. All right, which will be mainly used as a switch in most of the applications, right? So, so in the previous sessions, we have discussed like we came to know different turn-on mechanisms, and in the previous session we came to know about the commutation circuits, that is the circuits how to turn off the device, right? So in this coming sessions you will be learning about the trigger circuits. So different turn-on methods we have already aware about. Okay, let me ask someone. Let me ask someone to give me. Hanisha, are you there? Can you come in? Hanisha. Hanisha. Yeah, she's not there. All right. Okay, Hanisha not there. Let me check. Shama Shetty, are you there? Shama Shetty.
Hello, ma'am.
Okay. Can you give me different turn-on methods? Just list them. Can you recall things?
Um,
Yeah.
um, I,
I'm asking about what are the different ways to turn on. We had listed few methods. We came to know about different methods that can be used to turn on SCR.
forward voltage triggering.
Okay, you got the message?
Then, no,
Okay, okay, good. Yeah. Forward, yes, correct. Forward, correct. Forward
one
voltage
one
triggering.
method is temperature one.
Yeah, yeah. Thermal triggering. Yeah. Increasing the temperature. Exactly correct. Then, so that should
Uh,
give you the remaining. Yeah. Hint for
light one. Light.
light or radiation. Exactly correct. Then, two more.
I don't remember.
You don't remember. Okay, fine. So there were dV by dt triggering, that is controlling the voltage across junction K2. Yeah. So then the last one was gate triggering. Okay. So we
Uh,
have, yeah, fine. Yeah. Thank you, Shama. So we had come to know about the different methods. So here in this session, we'll be discussing um, gate triggering in detail, because that is an important part of this SCR, because we know that the SCR, its application lies in its important feature, wherein with small control signal it can be triggered, it can be fired, or it can be turned on. So SCR will change its mode from non-conducting to conducting with the small control signal that we apply at the gate terminal. Okay, so we will be discussing the resistor triggering circuit in this session. All right. So there are different ways. The different circuits are resistance triggering circuit, resistance capacitance, which we commonly call RC triggering circuit. Then we sometimes use UJT based triggering. Then there is IC based triggering as well. Okay. So we'll be discussing all these one by one in the coming sessions. So as it is displayed in this slide, you can see that many of these circuits are not sophisticated and not used practically, all right? Not all, not all. But these circuits help us to understand how the resistant triggering circuit would work, or the RC triggering would work, something like that, okay? So it will give us a brief or a broad idea about what is this triggering circuits are, right? So we will move on to resistor triggering circuit. So mainly, triggering circuit means what you should visualize. You should understand that this is a small triggering circuit, or alteration or moderation in the circuit, where you design in such a way that it will provide the required control signal at the gate terminal. Okay. So here is our SCR. You know, this is anode, this is cathode, and here is our gate terminal. So in applications, wherever you are using SCR as a switch, so to turn it on, there are different methods, right? You can either increase the voltage that you apply across anode and cathode. Okay, when you cross breakover voltage, obviously the device will turn on, but which is not recommended, right? So in order to turn on the device at earlier stage or with the lower supply voltage that we connect across anode and cathode, we use this gate triggering circuit. All right, that means we give control signal at the gate terminal. All right, what is this control signal we are talking about? These are nothing but the voltage or in turn the current that will be applied to the gate terminal so that it will turn on. Now at this point you should be aware that if we give a signal here, if we pass gate current, what happens internally. So you should be aware at this juncture. We are not going to repeat all those things now. All right, because in the previous sessions we have already discussed what happens when a gate signal is given here. All right, so now in this session we'll be discussing how this R triggering circuit works, right? So now you have to recall all the specifications that will be mentioned by the manufacturer. If you recall, a manufacturer will provide the minimum gate voltage that is required to turn on the device, the maximum gate voltage that should not cross so that it will not damage the device. The manufacturer will also specify what should be the minimum current that should be applied at the gate terminal, or what is the maximum range that should be allowed to pass through this gate terminal. So all these ranges, power dissipation range, all these ranges will be specified by the manufacturer. So based on that, we have to design the circuit so that it will provide sufficient control signal, which is nothing but it can be voltage or the current that will be connected to the gate terminal. Okay. Now, as you can see, our triggering circuit, the simple circuit, it looks like this. You have the AC supply here, the load is connected here, okay, and you have the SCR. So here at the gate terminal, what you have the circuit is your R triggering circuit. So there is resistor R1, R2, and R. R1 is the current limiting resistor and R2 is the variable resistor, which actually will control the signal that will be applied here. And there is a diode. The diode is just to avoid any reverse current that can be that would be flowing to the gate signal. Okay, just to avoid that, the diode will be provided. And R is the stabilizing resistor. Stabilizing resistor meaning that it stabilizes or maintains the voltage that will be coming across or to this gate terminal. Okay, so we will understand how it works. So all these points I've just now mentioned there. So it is a simple triggering circuit. The limiting triggering angle here, the triggering angle, what we call it as alpha, it is between 0 to 90. You cannot cross 90 there. I will explain what does it mean there in the coming slides. Okay, and the performance obviously depends upon the temperature and the SCR characteristic. That is the rating of the SCR. What type of SCR you are using, what are its rating and all. It depends on that. Okay. Now, as I mentioned, R1 is the current limiting resistor, R2 is the variable resistor, and R is the stabilizing resistor. Okay, R2 is the resistor which controls the firing angle, and we will describe what it is. All right. So now imagine when if R2 is 0, that is this variable resistor what you have, it is 0. All right. Then R1 should be such that, okay, if R2 is 0, R1 will be the one that will be controlling the current, right? So R1 should be such that it should not cross the maximum permissible gate voltage, okay, specified by the manufacturer. Okay.
Excuse me, ma'am.
Yes.
Ma'am, the streaming has not started yet. There are a few people who just told that right now.
I think they have to just log in there with that link.
Yeah, but then it shows that streaming has not started yet.
All right. How is that? We have already started, right? Let me show. Okay, now it would be. One second, we'll wait. Just it is starting now. Okay, fine. I think now they will be able to. Please inform them to join in.
Yes, ma'am.
Okay. Okay, informed? Informed, Legina? Yeah, fine. Okay, then maybe should I wait for them to join in and then continue, or what is it? 101 are here. Let me just wait for another 1 minute. I'll see if the count increases, if more people join. See, this is what happens if you're not punctual, you'll be disturbing others. No more people joined, right? It is showing 101.
Ma'am, it's not available, ma'am.
It's not available, is it? What is that, Sudeep?
It says this stream is not available to your organization.
Oh, how is it?
Like, actually, I was waiting there. I didn't know that we are meeting in Google Meet itself. So then I joined later.
Uh-huh.
Now I verify it shows this stream is not available to your organization.
No, what does it mean? Like, where I got that link from this meeting itself, and that is what I have shared.
I
Okay,
don't.
maybe, okay. Maybe you can just text your friends saying that the recorded video of this live session will be shared later. They can watch later. So if they're late to join, then maybe that is a punishment for them. They cannot be there in live session. Or let me check. Yeah, 100 people is maximum that will be allowed here in the meeting, and that was what the alternate I had got it, that the live stream link has to be shared, and I don't know what's the problem. So, all right, maybe I will text that in the group saying that maybe another 20 students. Fine. Fine. Okay. Let me plan Zoom from next week onwards. Okay. Yeah. So this week, remaining 18 students may have to watch the recorded one. All right. Okay. Just inform that message to your friends. Shall we continue? Okay. So I was here. I was mentioning like. If R2 is 0, then R1 resistor will be the one which will be controlling the current here in the circuit. So R1 has to be selected such that the value of R1 should be selected such that it will not cross the maximum permissible IG, that is minimum gate current. Okay, so if you can observe that the current it should be less than Vm by R1. What is Vm? Vm is your maximum voltage of your input, that is magnitude of your input, right? And R1 is the resistor. So based on this equation, R1 should be selected such that it will not cross the maximum permissible gate current. All right. So then about R, that is stabilizing resistor. Stabilizing resistor should be again chosen in such a way that its value again should not cross the maximum forward gate voltage. If you observe, go back to the circuit. So this stabilizing resistor R should also be taken care and this value of this R should be selected in such a way that it will the voltage that would be provided here across R will not cross the maximum permissible voltage. So how do you calculate the voltage here? You will use the voltage divider network, right? So based on that, VGM maximum permissible voltage at the gate terminal would be given by this term, which is your voltage divider equation. So from that, R1 should be selected less than this value, all right, when R2 is equal to 0. Okay. Now, if you observe, the gate trigger circuit always draws the current based on R1 and R2, right? And also by R1. So the voltage that will be provided will be via this diode, all right? So the current that will be passing through the diode, because it is forward bias now, it will be allowing the current to flow to the gate terminal, all right? Now what about R2? There are different situations or conditions about R2. When R2 is a minimum, that is 0, or when R2 is maximum, or R2 is, say, at some value. I said R2 is the one that will be controlling the control signal, okay, at the gate terminal. Control signal in the sense, the voltage that you are applying to the gate terminal, or in other words, the current that is coming to the gate terminal. So if you are talking about, say, the pulse signal or the signal that is coming here, so at what instant is it appearing at the gate terminal, that will give us the alpha angle or the triggering angle, okay, alpha or the triggering angle or the firing angle, okay, all meaning same. It is nothing but the instant, that is from 0 instant and the time at which the control signal appears at the gate terminal, all right? So this alpha angle, at what time the signal is appearing at the gate signal, is controlled by R. So based on the R value, the control signal or the firing angle also will be varying. So let us observe how it varies, all right? So first case is when R2 is very large. When R2 is very large, okay, what happens? If R2 is large, what happens? The current will be small, right? Obviously, right? So I should have put the circuit here. I'll go back. When R2 is very large, so the current coming at this part will be small, okay? So obviously the voltage that will be appearing at the gate terminal will be small because V is equal to product of I and R, right? So VG also will be very small. Say if this VG is very less than the specified voltage that is required to turn on the SCR, then the SCR will not turn on, okay? Now I have given here the condition. If VGP is less than VGT, VGT is my gate voltage, T stands for threshold, threshold gate voltage. If it is specified by the manufacturer, say this is the value at which the SCR will turn on, and if from the circuit, if the voltage that is coming at the gate terminal, if it is less than the specified range of voltage by the manufacturer, then obviously the SCR will not turn on, okay? And obviously there will be no output or the current at the load. And the supply voltage will appear at the SCR. Let us observe the waveforms. See, I bring to your notice that in power electronics, all explanation circuits will be explained using waveforms, all right? Power electronics is nothing without waveforms. So you should be able to represent or give your answer, explain your answer with respect to waveforms. So I suggest you practice drawing waveforms, all right? Now let us describe the case 1 condition when R2 is very large, okay? So this is your input, Vs is your sinusoidal input, all right? Now say imagine this dotted line is the threshold gate voltage that is specified by the manufacturer. All right. So at this level, the SCR will turn on. That is what specified by the manufacturer. Now, based on this circuit, okay, now R1 is your current limiting resistor and R2 is the one which is controlling the alpha angle, right? So based on the value of R2, you will get the voltage that is coming at the gate terminal. All right. So now imagine R2 is very large. If R2 is very large, then the voltage, we will call it as VGP, that is coming at this point, will be small because the current coming here will also be small, right? So observe here, our VGP is somewhere here, right? So it is not equal to, or it is not reaching the minimum requirement that is specified by the manufacturer. That happens, the SCR will not turn on. So if there is no control signal at the gate terminal, SCR will not turn on. So observe voltage across the load. V0 is nothing but voltage across load, and I0 is the voltage across, current across load. VT is the voltage across SCR. Okay. Observe, V0 is 0, I0 is 0, and voltage across the SCR or the thyristor will follow the input. So whatever the input is coming, that will be across your SCR. Are you with me here? Till here? Any clarification, any doubt? If it is okay, I'll proceed. Or maybe I will ask someone to explain the next two cases. Are you with me? No response. Okay. Fine. Okay, let me ask a question. Whom shall I ask? Let me see if you are listening to me. Prima D'Souza, are you there? Sorry. Prima D'Souza, are you there? Prima, yes, you are there, but you are not attentive, you are not listening. Okay. Priyanka? Priyanka, you are there? Priyanka, you are not there. Okay. Anisha? Anisha, you are there? I think you answered me earlier. Anisha? So yes, she has not joined. Chaitanya? Chaitanya. Okay, so yeah, some action has to be taken with these. Sushma? Sushma? Come in. Sushma, you are there? What's the problem with these guys? I don't understand. Catherine, you are there? Catherine? No, she has not joined the meeting at all. Okay, okay, fine. All right. So I would like to bring to your notice, I just now mentioned that since the SCR has not turned on, okay, the load that is connected in series with the input, all right, okay, you can observe here the output voltage is showing 0 and the output, load current or the output current is also shown as 0, okay, and the voltage across thyristor or the SCR is same as the input, all right. Just be sure that it's not exactly 0. The voltage across the load will not be 0 and current also will not be 0, but there will be minute voltage across the load. Minute in the sense, say around 1 volts, right? And just for your recall, we are talking about our electronics application where the voltage that can be handled by the would be, say, from 200 to 300. It can go further based on okay, fine. About watching. So now I'm able to watch live stream. Valona, is what you want? Yes, okay, fine. Okay, fine. So I was in here. Okay, I was explaining. So the voltage across the load will be very minute. That is 1 or 2 volts. So when we are discussing the application of power electronics, where we are talking about voltage range of higher value, say 200 or 300, based on the specifications of
Ma'am,
the
your voice is breaking.
I don't know what the problem is. Wi-Fi. So I have good Wi-Fi connection here. Is it still breaking?
Yes, ma'am. It was clear before, but suddenly it started breaking right now.
Okay. Should I shift to mobile data? One second, please hold on.
Yes, ma'am.
Okay, I'm shifting to my hotspot. I don't know whether it will be. Oh, am I out? Are you there? Am I still with you?
Yes, ma'am. You're audible right now.
Is it clear now? My voice?
Yeah. Yes,
Yeah.
ma'am. Yes, madam.
Okay. I shifted to my mobile data. Fine. So screen is still visible, right? There is no problem with that?
Yes, ma'am.
Okay, thank you, Astrid. Okay, so okay, so the voltage across the load will be small. That's why it is very negligible compared to the range of voltage that is handled by SCR. So it is shown as 0. Okay, so just be aware that it is not 0, but it is, since it is very negligible, it is shown as 0. All right. Okay, so coming to the next condition, when alpha is equal to 90 degrees. 90 degrees in the sense, when this voltage, what we are applying at the gate terminal, if it is equal to the threshold gate voltage, then our alpha will be exactly at 90 degrees. Okay, so that is when the voltage coming at this point, if it is matching with the threshold gate voltage that is specified by the manufacturer, then we say VGP will be equal to VGT. Okay, so if our VGT is the threshold voltage and if VGP is equal to that, then the voltage, okay, which is sinusoidal here again. So when it reaches equal to VGT, then the SCR will turn on. So when the SCR turns on, observe what happens. All right. Now observe here, the gate voltage is increased. At this point, it is equal to VGT. That is the point where SCR will turn on, or it will trigger, or it will fire. Okay. Now observe the voltage across SCR. Till the SCR was not turned on, it was following the input voltage. Okay, The moment the SCR is turned on, observe at this point, now the voltage across SCR has dropped. It will be minimum or it will be almost zero. Now, as we have just now discussed, it will be around 1 to 2 volts, right? When it is turned on. So because it is very negligible, we are showing the waveform as 0. Okay. Now in the reverse apply voltage, you know that SCR will again turn off. Okay. So voltage across SCR will be following the input. Now observe the voltage across load and the current across load. Okay. So till the SCR is turned on, till it is not turned on, the voltage across the load is 0, even the current. Okay. The moment the SCR is turned on, the voltage across load can be observed here, which is following the input. Obviously, the magnitude will be varying. All right. So we will not go into the expressions there, derivations and all. For your syllabus, it is only given to understand the circuit and explain how the circuit works. All right. So those who are interested, we can, if you are interested to know the magnitude or the expressions derived here, you can get back to me. I will give you the information. Okay. Now, just at this moment, understand the working of the circuit. All right. I hope it is clear. Is there any doubt at any point? Are you with me? Are you with me? You are able to follow? Okay, thank you. Okay, yeah. Now, so in the last condition, when our voltage that we have applied across the gate terminal, if it is crosses, if it is more than the threshold voltage specified, then what happens? Alpha will be always less than 90 degrees. All right. So less than 90 degrees means it can vary the alpha. This is our alpha. Okay. The firing angle. I told you the angle at which the SCR will turn on from the reference, that is 0 reference. The moment the SCR turns on, that will give us the firing angle or the alpha. Okay. So this alpha angle, if R2 is decreased, you are reducing the R2, then it can, if the VGP, if it is greater than the VGT, when you are reducing, going on reducing the R2, if VGP is greater than VGT, then alpha will lie between 0 to 90 degrees, right? So minimum will be 2 to 4 degrees. It can never be 0. All right. So we have a setup in our laboratory where you can observe this triggering circuit. All right. Maybe once you come back to college, we'll have a look at that, where you can observe the alpha angle, that is firing angle, varying as you vary the variable resistor. All right. So based on that, you have a relation given here. VGP sine alpha is equal to VGT. So alpha will be equal to sine inverse of VGT by VGP. All right. Since VGP we know, because of this voltage divider network, we got this expression. Substituting VGP, you will have alpha is equal to sine inverse of this expression. Please note down the expression. And if you observe from this, all parameters except R2 are all fixed. Okay, so which means R2 is the one which is controlling the alpha or the firing angle. I'll just give you a moment to note down all these things. Then I'll move on to the waveform description for third case 3. Okay, if you're done with that, we'll move forward. So observing the waveforms for condition case 3. Now what happens? Imagine you have decreased R2 further. Here is our R2, which is a variable resistor. Okay. So if you are decreased further such that your VGP is greater than VGT. So when you are decreasing R2, obviously current will increase. So when current increase, obviously the voltage VGP, what we are talking about, VGP, so that also will increase, okay? So if that VGP is more than the specified threshold voltage specified by the manufacturer, then the SCR will turn on faster or sooner, okay? Say this is the range. The dotted lines are not shown here. This, I hope you're able to see my mouse moving, okay? If this is the range where VGT is specified and the voltage coming at this point, VGP, if it is of this magnitude, but your VGT is somewhere here, then the SCR will trigger at this point itself. Correct? I hope you're able to understand. So based on the value of R, you can control at what moment or what instant you want to trigger or turn on the SCR on. Okay. Now, if you observe the responses, if you observe the voltage across load and current across load, now observe the voltage across the load is starting from this moment, the moment SCR is turned on, and it is following the input. Current is also following, but with lower magnitude, obviously. Then voltage across SCR, if you see, till it was not turned on, it was following input. The moment SCR was turned on, the voltage across SCR will drop, okay? And in the reverse cycle, we know that SCR will be off, so it is following the input. So similarly, it follows in a similar fashion till your VGP, okay, it is say at point where it is equal to or say more than VGT, the specified VGT threshold gate voltage, then the SCR will turn on. All right. Now, what do you observe from these waveforms? Now, let me show you case 2 waveform. Observe the waveform output here. This is your case 3. Observe the output. So, what do you think? What is that you can control by SCR now? I will show you the waveform for case 2. I'll show you the waveform for case 1 as well. In case 1, obviously, there is no output at all. This is your case 2. Observe the output. Okay. And case 3, observe the output. So can you see that with the alpha angle, you can control the output power across the load, right? Yeah. So here, if you take the instantaneous output voltage, if you measure that input output voltage across the load, okay, observe the case here and here. So lesser the alpha angle, more will be the power that you can observe at the output or the load, right? So alpha, that is the moment you control at what moment you are turning on your SCR. So based on that, you can control the output voltage as well across the load. So which means that how much of power is it available at the load, that can be controlled by the time at which you are turning on the SCR. That is the point. Okay. All right. So finally, actually, this is a circuit that is used in the textbook. I've just put it across so that you will not get confused. This is the circuit. It is same, not much different. It is not at all different there. Only the alignment of the components are shown in a different way. That's all. So the circuit is same. All right. And this is the waveform that is shown in the textbook. Your textbook doesn't show you the gate voltage or the voltage across the output, that is current across the load and all. Here you can see ESC is nothing but your input voltage. EL is your output, that is voltage across load, and VAK is the voltage across the SCR. So if you observe, initially till the SCR is not turned on, the output across load will be 0. The moment you turn on, so here the gate signal is not shown here. So that may be a little difficult to understand, but I have explained that using all these waveforms. So at this moment, you should be able to interpret the textbook, all right? So the moment the SCR is turned on, the load across the, output across the load will be following the input. So once the there is reverse voltage at the input, the SCR turns off. So output at the load also will be 0 at this moment. So if you observe the voltage across SCR here, till it is not turned on, it is following the input. The moment it is turned on, it is the voltage across SCR is small, negligible, but here it is shown as 0 because it is very small. Okay, and in the reverse, it will follow the input because it is turned off. Okay. Now, this is an expression, please note down, at which the thyristor will turn on. Thyristor will trigger when the instantaneous anode voltage ES is equal to IG minimum into RV plus R minimum, where RV is our R2, that is variable resistor. R minimum is nothing but R1, which we have discussed in our circuit. Okay, that's all. That's the only difference. R minimum is R1 in our circuit. RV is the R2 in our circuit. RB is R in our circuit. All right. So this is the expression where IG minimum is your minimum gate current. Okay, that will be specified. PD is the voltage drop across the diode. Okay, and VG minimum is again the minimum gate voltage that is required to turn on the thyristor or the SCR. Please note down the expression. I will give you a minute of time to note down. So this is nothing but at what instant, that is at what time of the input, the SCR will turn on. Okay, so if your circuit values, that is the resistor values, are such that it is matching with the minimum gate current specified by the manufacturer, it is providing the voltage which is matching the minimum requirement that is specified by the manufacturer, then at that instant your SCR will turn on. Okay, I hope you are with me. I hope all are with me. You are able to follow. Please respond. You're with me? Okay, fine. Okay, fine. All right. So this is a problem I want you to solve right now. I want you to solve right now and give me the answer. Yeah, fine. Okay, thank you. I want you to solve this problem and give me the answer. Thank you, guys. It's okay. Thank you. Now try to solve this problem. The circuit is the same circuit what you have noted down, I assume. Okay. Uses an SCR with IG minimum equal to 0.1 milliamps and VG minimum is given as 0.5 volts. And the diode that is used in the circuit is silicon type. And the peak amplitude of the input is 24 volts, peak amplitude of the input. All right. Now what is asked? Determine the trigger angle alpha for RV. So in our case, RV is nothing but R2. All right, 100 kilo ohms, and R minimum is R1 of 10 kilo ohms. I have given you an int. ES, since the input what is specified here is a sinusoidal input, okay, so it obeys the expression ES is equal to E max sin omega t. So I have given you one hint there. So try to solve. You have all the components here based on the expression what you copied just now. See here, ES is equal to IG minimum into RV plus R minimum plus VD plus VG minimum. So everything is given. IG minimum is given, within the brackets RV plus R minimum is given, plus VD. What will you substitute for VD? What will you substitute for VD? VD. 12. What is 12.7, right? It is a silicon type, correct. Okay. So it's a silicon type of diode. Okay, I got the answer. So the cutting voltage of silicon diode is 0.7. So 0.7 is required to forward bias or make the diode conduct. So that will be the voltage across the diode, 0.7. And VG minimum is also given 0.5. So why is this peak amplitude of the input given? Where do you use that? Why is that given in the expression? Now I have given you the hint. ES is equal to E max sine omega t. Correct. E max is nothing but 12. Correct. Exactly correct. Yeah. So how to get alpha? Now from this expression you will calculate ES. Okay, you will get some value. All right. E max is already given. E max is given in the problem, that is 24. All right. And sine omega t. Omega t is nothing but what? 2 pi ft, right? Our 2 pi ft is nothing but the angle. All right. Now in our case, the angle what we are talking about is nothing but the firing angle or the triggering angle. So you can rewrite this expression as ES is equal to E max sine alpha. So the 2 pi ft, the phase angle what we are talking about here, is nothing but our firing angle alpha. So substitute 2 pi ft is equal to alpha, or you take this expression as sine alpha. So from the previous expression you will calculate ES. E max is given, sine alpha. So what is asked is determine triggering angle or the firing angle alpha. So what's the value you are getting? What is the answer you're getting? What is 4.588? Yes, it is 30.55. Correct. Exactly correct. Correct. Yeah. Got it. So yes, you will get it as 12.2. Yeah, got the answer. ES is equal to 12.2. All right. And E max is 24 sine alpha. So in that expression, you have to find alpha. So rearranging, alpha will be equal to sine inverse of the bracket. Within the bracket, you have 12.2 divided by 24. So that will give you 30.55 or 30.6. Okay. So I hope it is clear. We have come to end of the session.
Hello, ma'am.
Yes. Sagar,
Ma'am, I
yes.
had a doubt, ma'am.
Go ahead. Yes.
Am I audible, ma'am? Ma'am, can you go to
Go
that
on.
circuit, ma'am?
All right. First slide here.
Yes, ma'am. Yes. In this, what if the current through the diode D is sufficient enough to switch it on and even switch on the SCR? What is the dependency over the frequency of the input signal? If the frequency is too high, then even if SCR is getting the current, it may not get current for sufficient amount of time to turn it on. It might be a small spike of current coming through it, but still it might not switch on the SCR. So what is the limitation over the frequency of the input? Will maximum frequency, very high frequency, will it turn SCR on even if the time is not sufficient?
I think let me put across your question. You are saying like what would be the frequency and will it affect the turning on and off of the SCR? Is it so?
Yes, ma'am.
Or
Yes.
is it the frequency affecting the SCR turn
Yes.
on and off, right?
Yes.
Yeah,
Even
exactly.
at very high frequency, we know that through diode also there will be an interelectrode capacitance arising. So what is the dependency or frequency in the circuit? What is the limitation or the frequency range?
I mean, first of all, understand that these are not practical circuits. Okay, I'll come to your question there. First of all, these are not practical circuits. All right, these circuits are only to understand the basic theory of the triggering circuit. All right. Now coming to your
Okay.
point, coming to your point here. Even if the signal that is coming, it may be say the voltage or the current what you're talking about, even if it is spike, okay, even if it is spike, if that voltage, this magnitude of the voltage of that spike, if it is falling within the threshold specified by the manufacturer, that will turn on. All right. If it is below, if the magnitude below the specified range, then the SCR will not turn on. All right. And coming to your next point, what about frequency at which it is getting turned on? Yes. The next moment it will turn off, right? Because the input is sinusoidal. So every cycle, if the voltage coming at this point is sufficient enough to trigger it, it will fire it, and in the reverse cycle it will turn off. So it will be like switching on and off. Got it?
Okay, ma'am. So there is no minimum duration for which SCR should be getting the signal through gate to
Again,
turn
see,
it on.
again, it depends on your application, how long you want to keep the SCR on. Okay, so based on that, again, your circuit will vary. Now, again, this limit your understanding only for this triggering circuit. How do we trigger it? Okay, now for what duration we want to keep the SCR on for our further applications? Okay, that is the next part.
Okay, ma'am. Okay.
I hope I'm able to convince you.
Yeah.
Sagar.
So for high frequency applications also the circuit is valid, right, ma'am?
It is valid. It is valid, provided
Okay.
the current coming at this point is meeting the standards requirements.
Okay, ma'am.
Got
Okay.
it?
Thank you,
Yeah.
ma'am. Yeah, ma'am.
Yeah. Okay. Thanks for all these discussions. Yeah. Okay. Any other doubt? Any other doubt? I hope the triggering circuit is clear. Mainly you have to consider the three different cases there, case 1, case 2, case 3, as we have just discussed. Please go through. I will share the slides in Canvas. The points mentioned here may not be enough to make you understand the circuit, which means that you have to go through the textbook. Again, even in textbook, if you are not familiar with the previous topics, you will not understand anything. Let me warn you, because all these are continuity. I hope you are able to understand. Okay, all topics are linked together. If you don't know what is the turn on procedure, what are the specifications that we are talking about, what are the different ways to turn on or turn off, then only then you will be able to understand the present topics. Okay, if there is no link, let me warn you, you will not understand anything. Okay, and just to remind you, all the explanation of most of the power electronic circuits you have to represent with respect to waveforms. Okay, just practice them. Practice how to draw waveforms wherein every component should follow based on the input. Okay, so practice waveforms. All right, we'll end the meeting here. I hope it is, yeah, yes, thank you. I'll stop recording and I'll stop streaming as well.